Suppose we have a picture of a blackboard from an angle in 3 dimensions so that the blackboard appears like a parallelogram. And we want to apply a transformation to the pixels of this image in such a way that this parallelogram is mapped to a rectangle. We can do this with a linear transformation. And since the pixels on the page live in a 2-dimensional space and a 2-dimensional linear transformation is specified by the destination of 2 basis vectors, we can choose 2 basis vectors however we want on the left-hand side and specify where they go on the right-hand side, and that will determine a linear transformation. The most natural choice of vectors in this picture is to map this green vector running along the bottom of the blackboard to the corresponding vector along the bottom of the blackboard in the right-hand picture, and similarly for the vertical vector. And to find the actual linear transformation, we would need to specify some coordinates for these vectors. For example, this vector might be 0, 1, in which case this one would also be 0, 1, and maybe this vector is 2, 1, in which case the green vector on the image side, in order to have the same length, would be square root of 5, 0. We can set up a system of linear equations for the entries of the matrix in order to find the linear transformation that does this. So the matrix is minus square root 5 over 2, 0, minus 1/2, 1. We're given that T is an injective linear transformation and that V1 up to Vn is a linearly independent list of vectors in its domain. We want to show that the images T of V1 up to T of Vn are also linearly independent. To begin, we unpack the definition of linear independence. It means that whenever a linear combination of the vectors is equal to 0, the weights were all 0. In order to prove an if-then statement, we assume the if part and reason our way to the then part as a conclusion. Assuming that a linear combination of the t's is equal to 0, we can rewrite this equation by saying that t of c1 v1 and so on up to cn vn is equal to 0, since t is linear. Then we know that t maps the 0 vector to the 0 vector and that t is injective. So the 0 vector is the only vector that t maps to the 0 vector. Therefore, this vector inside parentheses on the left-hand side is necessarily equal to the 0 vector. But since the v's are linearly independent by assumption, the only linear combination of them which is equal to the 0 vector is the one with all weights 0. Therefore, the list T of V1 up to T of Vn is linearly independent. In this problem, we're asked to investigate the behavior of Julia for solving linear systems of equations. Let's start with a simple system like x plus y equals 2 and x minus y equals 5. The matrix of coefficients for this system is 1, 1, 1, minus 1. And the vector on the right-hand side is 2, 5. We solve this system by calling the backslash function on a and b, and it returns 3.5, negative 1.5. We can check that this solution is valid by calculating a times x and check that we do indeed get 2, 5. If we call this backslash function on a matrix that isn't invertible, then we get an error. In this problem, we're asked to investigate an iterative approach to finding the lead eigenvector of a random matrix. This matrix is populated by filling in random numbers along the diagonal and below the diagonal and filling in the entries above the diagonal to enforce symmetry. This is what the random matrix looks like. To find its lead eigenvector, we start with a vector which is 0 in every position except the first, where it's 1. Then we repeatedly replace v with AV and then divide out by the norm. We can compare the result to a direct calculation of the eigenvectors using the built-in eigenfunction. We can see that the entries we got from our result are up to sign and some small numerical error, the same as the eigenvector in the last column found by the system. The reason this algorithm works is that the eigenvectors of A form a basis for Rn, so we can write any starting vector as a linear combination of those basis vectors. Then repeatedly multiplying by A results in each term gaining an additional factor of the corresponding eigenvalue. Intuitively, the first term here is much larger than the other terms if lambda 1 is the largest eigenvalue. One way to show this rigorously is to divide both sides by lambda 1 to the k and take k to infinity. Then we can write the ratio of a to the k v0 by its norm as follows. As k goes to infinity, this converges to c1 u1 divided by the length of c1 u1. In other words, it converges to the leading eigenvector normalized to have unit length. There are starting vectors that would cause this argument to fail, namely those for which the component c1 in the u1 direction is equal to 0. We can use this idea to come up with an algorithm to find the second leading eigenvector, namely we start with an eigenvector which is orthogonal to u1 and apply the same algorithm.